Today we'll start our first class on statistical mechanics. So statistical mechanics. So so today in our class we will mostly discuss about this some concepts about the uh, random walk problem. Second is on probability. Probability means this concept of probability is itself in there in the random walk problem. And third is the uh, about the micro and macro states, which is a very important concept in statistical mechanics. Okay, so so these are basically the topics that uh, we will study in today's tutorial session. Okay, so and if time proceeds, we will also discuss about some problems from previous assignment problems. Okay, like previous assignment 2 or assignment 3. So let's start from question number 1. Okay. Suppose in one dimensional random walk problem for a walk in 4 steps, that means n equal to 4, if one take 3 steps forward and 1 step backward, then the probability of taking 3 steps forward will be equal to option A was F2 4, option B F4 2, option C F4 minus 2, option D F minus 2 4. So and the information provided here is, suppose with every step you will flipping a coin. So this basically means that the probability of moving either in the left side, forward side or backward side will be equal, and that will be equal to half. That is equal to the probability of getting head or tail when you flip a coin. Okay, so before solving this problem, let me first discuss about what is a 1D random walk means. Okay, I mean random walk also exists for 2D and 3D also, but for this problem we will only consider the 1D random walk problem. Okay, so so this is basically, let's suppose this is a line, this is the origin O. So let's suppose a variable, let's x, which can move either in the, let's suppose this is the forward side, this is the backward side. Okay, or this is the right side, this is the left side. Okay, so these are the steps along this line. Okay, so the probability, like for a 1D random walk consists a variable or a walker that starts at an initial point, initial position. Here the initial position is the origin here, and so that is that x equal to 0, and it can move, and it can move in left, that is -1 step, or right, that is +1 step, at each time with equal probability. So equal probability will be only the case when the random walk is not biased. If it's a biased random walk, then a specific direction will get a higher probability. Okay, so for this problem we only consider unbiased random walk. Okay, so for simple case, so in simple case, that is unbiased random walk. That means the probability of either moving in right or left are basically equally to each other. So unbiased walk uh, at each time step the walker moves either in the right side, that is +1 step, with probability equal to half, or equal to left side, that is -1 step, that is equal to half. Okay, so for a 1D random walk problem, so the probability of moving this side, let's say p is half, or if it's moving in opposite side, this is also half. So in this way the total probability will be 1. Okay, if it was a 2D random, if there was, suppose 4 direction was there, this, that means it's now become a 2D random walk. In that case, the probability of moving each side will be 1/4. Okay, 1/4, 1/4, and 1/4, so that the total probability will become 1. Okay, but since it's a 2D problem, so moving each side, the probability has a value of half. Okay, now so this is the probability P and Q. With moving right side, P equal to half, and left side the probability Q is half. That is for unbiased problem, it's equal to each other. Now so after after taking n steps the total so let's suppose that if you take like when you move each step, let's suppose you are like moving like around one step, so the total amount of displacement in that case will be xn. After taking n steps, xn will be summation of I equal to 1 to n si. So si is basically si can take value plus 1 or minus 1. Okay, so this will be the total displacement. Okay, total displacement. So uh, but in this case ESA is basically independent of like whatever the values of the displacement is. And next thing is the mean. Okay, so mean is basically, let's denote mean as sigma here. So mean sigma will be, so if you are moving a large amount of step, then the mean should be equal to 1. Sorry, mean should be equal to 0 actually. So this is the value of mean for ideal case. Okay, and uh, that is basically the total mean displacement. Okay, mean displacement. Hmm. Now after this, let's just discuss some of the properties of random walk. Okay, so properties. So so basically random walk actually obeys the properties of a binomial distribution. Okay, so uh, after n steps, so let's suppose if x is your variable which is moving in this 1D in this 1D line, then after n steps uh, the probability of x follows the binomial distribution. So px would be simply nk. So I hope you guys already know about like properties of a binomial distribution. So px would be simply nk p power k and q to the power n minus k. Okay. So where k is the number of forward steps and n minus k is the number of backward steps. Okay, so if let me just describe this thing once again. So if suppose the x variable is taking n steps, so total number of steps is n, and the probability of out of that n step, k step is will be in the right direction and n minus k will be into the left direction, will be we will following this formula, I mean following this distribution. Okay, okay, so this is basically the binomial distribution. Okay. Hmm. the expected position. Next property will be the expected position. So expected, so this is the distribution, probability distribution. Next is the expected position. So expected position, expected position will be e to the power x n, that will be p minus q n. Okay, so after taking the n step, the expected position of the variable should obey this formula p minus q n. So for an unbiased random walk, if p equal to q equal to half, in that case the expected value will be simply 0. So this means that the expected position is nothing but the mean position. Okay, for an unbiased random walk, the value will be simply 0. Unbiased random walk. Now is the mean square displacement. So this is basically the mean. This is basically the mean. Next is the mean square displacement. Mean square displacement. So mean square displacement will be simply now what you have to do right now. So so mean square displacement. So if you calculate the mean square displacement of this 1D random walk, that means basically the square of the displacement, take the mean of the square of the displacement, each displacement, and that value would be simply n. Okay, so this is the mean square displacement, this is the mean. Okay, so these are the some properties. Okay, that could be like, for this problem we may not need all this property, but this is like a very important things that you need to know, right, in future problems. If you solve any kind of problem which involve this random walk theory, then you have to apply all of these properties. Okay, and now we are coming back to our problem. Okay. Now Now for our problem, let's first write out what is the information that are given. Okay, so information is like given here that n is equal to 4, total number of steps is 4. So in each step it can it can move forward or backward. That means in our context it is like moving either right or left. Okay, so and here it is mentioned that it's a biased random walk. Okay, so probability of moving either forward or backward will be equal to each other. And in the problem it's mentioned that it can take 3 steps forward and 1 step backward. Okay, so this is like that means that from the n, the out of n steps, 3 steps will be forward and 1 step will be back. Then you have to calculate the probability. That means you have to use that binomial distribution function. Okay, so what is the like what is the probability of taking 3 steps forward and 1 step backward? So how to do that? Okay, so let me just write out what are the things that are given. So total number of steps is n equal to 4, and each step, that means moving forward or or backward with equal probability. Okay. In the problem also it's given that each that p is equal to half and q equal to also half. That means p is moving forward and q is moving backward. And as it's mentioned that each step you are flipping a coin, so this basically means that the moving forward or backward probability will be equal to flipping a fair coin. Okay, that flipping of a fair coin, we already know that probability is half, right? And next thing is uh, next thing is the worker takes 3 steps forward and 1 step backward. This is also a thing, like this is also mentioned. So now you have what these steps are given, and we have to calculate what is the probability of this particular occurrence, right? Now how to do this? So we already know this probability distribution, right? This is the basically the formula. Okay, so you have to use this formula. So let me write it once. Let me just copy it here. Okay, so this is the formula of use. Okay, so here n equal to, so here, so for, along according to this formula, n will be equal to 4, k will be equal to 3, p will be equal to half. That is stepping forward or backward. So now the binomial coefficient is let me write it like this, because there are three variable are mentioned here. So let me write it like this: p equal to k and n. Okay, so the probability will be p 3 comma 4 by 3 into p is half, k is 3, 1 by half into 4 minus 3. So this simply would be 4 4 4 4 4c3, that simply gives you 4 into 1 by 8 into half. So this gives you 1 by 4. So this would be the probability, right? 1 by 4. That is moving 3 steps forward and 1 steps backward. This will be simply gives you the probability. And but in the problem, what is mentioned? Ah, but in the problem we have to mention it in this notation format. Okay, so the format of this notation is like this, like if so this notation format basically gives you the probability function. Okay, so let me write it. So this notation f n k is the probability function. Okay, so here uh, this is the x. Actually x is the basically total displacement. So here uh, one second. So here n you already know, that is the total number of steps, that is 4, and x is basically total displacement. It moves 3 steps in the forward and 1 step in the backward. The total step will be 2. So the notation will be simply f4 2, and the probability will be 1 by 4. Okay, this is basically the answer. So here the answer will be simply this, f4 2. Okay, so I hope all of you understood how we are basically solving this problem. Okay, yeah. So basically what this problem basically gives is simply one dimension random walk problem. So this is basically a structure of a random walk problem. Okay, so this is a 1D line. So where if a walker starts from the origin, it can move either in the right side or the left side. Both are having equal probability of half in case of a unbiased random walk, and right side has p half and q half equal to half probability, because in the problem itself it is mentioned that with every steps I'm flipping a coin, and flipping, if you flip a coin, then either getting a head and tail has a probability that is half. Okay, so p and q is half, and after taking the n steps, this will be the total displacement. Okay, and these are the some properties, like the if out of the n step, if there is k steps are in the forward step and n minus k is in the backward step, then the probability will simply follow a binomial distribution, and this is the functional form of that binomial distribution. Next come the mean. The mean of the distribution is simply this, p minus q into n. This gives you the expected position, or the mean of the displacement for a like a very for a unbiased random walk problem. This mean will be simply equal to 0, and mean square displacement, that means if you take the square and then take the mean of the square term of the variable x, then it will gives you n equal to n, that is the total number of steps. Okay, so so this is some properties of the random walk problem in a one dimension. Okay, and back to our problem. So in our problem it is mentioned that we are taking 4 steps, and out of the 4 steps, 3 steps are forward and 1 step are backward. What is the probability? Okay, so we are using the same formula, binomial distribution formula. Here n is 4, k is 3, and p is half. Okay, that is the probability of stepping forward, backward, and q is also half. Okay, p and q both are half actually. Q is also equal to half. Okay, so this is it. Now the total probability. So as we know, the probability simply follows a binomial distribution, right? So P34, if you do the calculation, this gives you 1 by 4. And but in the question, it mean you have to find out the right notation. Okay, so like which will be the correct notation. Okay, to like justify this phenomena. Okay, so here in this notation, n is basically the total number of steps, x is the displacement. Here n is total number of steps is 4, and x is the displacement, total displacement, that is 3 minus 1, that gives you 2. So f4 2 is the correct answer of the problem. Okay, so problem number 1 is now finished. Now we will move to problem number 2. So problem number 2. Suppose you have three indistinguishable particles and have three similar baskets and have to place these balls in these baskets. Now, how many macro state and micro states are possible respectively? This is the problem. Okay, in the three indistinguishable particles are given, so that means the particles are basically identical with each other. You cannot just by the looks you cannot able to distinguish which is what particle. Okay, those are basically identical and you cannot able to distinguish them. And the question you have asked, uh, this three indistinguishable particle, you have three similar basket. So three similar basket, and you are placing these balls in this basket. So how many microstate and macrostates are possible? Okay, so these basically gives you uh, like microstate and macrostate means like the different combination. Okay, uh, what are the different combination that you can use, okay, to distribute these three indistinguishable particles into three similar baskets? Okay, these combinations are basically gives you microstate and macrostates. Okay. So that you have to basically calculate. Okay, and the options are given. Option A is 2 and 10. Option B is 2 and 8. Option C is 2 and 12. And option D is 2 and 10. So these are the all options given. So 2 means basically 2, the first number basically, this is the first number basically gives you the number of microstate, and first number gives you the number of microstate, second number gives you its corresponding no sorry, first number gives you the number of macrostate and second number gives you its corresponding microstates. Okay, and so okay, so basically let me just write the information, useful information. So given here is three indistinguishable particles and three identical baskets, beans, balls. Now calculate the number of possible macro states and microstates. Okay. So Okay, so uh, and before calculating, let me just briefly discuss what are the what are like in for our problem, what are actually the microstate and macrostate means. Okay, so let me write it here also. Okay, so hmm. So my mac in this problem, macrostate basically means the distribution, basically the distribution of, like, not different distribution, like different distribution basically denotes different microstates, different macrostate, or different distribution of particles among the baskets. Okay, this is a macrostate, and microstate means, under this macrostate, microstate means under each distribution, under each distribution, uh, what are the possible arrangement? Okay, like different arrangements under each distribution. Okay, this basically gives you the microstate. Okay, so under that particular macrostate. Okay, so now if you, so what are, so first, in order to, first you will calculate the macrostates. Okay, so so macrostates will be simply first distribution will be like this, like 300. 300 means all three particles in one basket. This is one distribution. That means this is one macrostate. Second macrostate you can consider 210. That means two particles in one basket, one in another basket. Okay, this is also distribution. Two particles are in one basket and another one is in any of the one basket. Okay, and third one is 1 1 1. That means one particle in each basket. Okay, so this is also a distribution that we can use. This is also a macrostate. Okay, 1 1 1, like one particle in each basket. These are the all the possible macrostates. So how many macrostates we are getting? We are getting total of three macrostates. Okay, now we are calculating the total number of microstates. Okay, so now comes the microstates. How we can calculate the microstates? Okay, so the microstate we have already discussed. This is microstate basically represent a specific way, a specific or unique way of, like, if you want to assign a particle into a basket. So if you consider each particle individually, so what are the different specific ways under distribution? I mean, following that way you can, like, distribute the particles. Okay, so this this number of ways basically gives you the number of microstates. Okay, so we can use a simple formula here to do this. So we already know, right? If suppose, so in order to calculate this microstates, we will just use a widely used formula in permutation combination. You already knows. If suppose there are n particles are there and there is k number of bins are there, then uh, the number of ways to distribute n particles into k bins will be simply equal to, simply gives you total number of microstates, right? So total microstates will be n plus k minus 1 into k, simply the combination of this n plus k minus 1, k minus 1. Okay, right. So this will be the total microstate for this problem. So for our problem, n will be simply equal to 3 particles, and bin is also 3, like 3 baskets are there, right? So total microstates will be 3 plus k is 3 minus 1 into 3 minus 1. This gives you 5c2. Basically 5 2 5. So this is 5 factorial into 2 factorial into 3 factorial. That is basically 5 into 4 by 2 factorial, right? So this gives you 10, right? So total number of microstate for this problem will be 10. Okay, so let me just tell you what you have done from the in this problem. Okay, so in this problem it is mentioned that you have 3 indistinguishable particles and have 3 similar baskets. Now we have to find out that we want to arrange these 3 indistinguishable particles in the baskets, and by considering it as a as a statistical system, we have to calculate the total number of macros, I mean the possible number of macrostates and microstates. So 3 balls are there and 3 baskets are there. Okay, so macrostate basically means here the different types of distribution of the particle among the baskets, and microstates basically gives you the different ways of arrangement. Okay, under each distribution you can arrange the particles in different ways, right? So each of the way gives you one microstate. So we have to calculate the total microstates for this problem. Okay, so first microstate is gives you 300. That means all 3 particles is in one basket. Okay, so that is a 300 condition, like where all the 3 particles are in one basket. The next macrostate will be 210, where 2 particles are in one basket and 1 particle is in another basket. Okay, that is also gives a macrostate. And third macrostate is 1 particle in each basket, 1 1 1. Okay, okay, so this is the total number of microstate. Macrostate will be simply 3, and now we have to calculate the microstates. Okay, so n is number of particles and k is the number of so we will simply use a in order to calculate the microstate, we will simply use a simple formula of combination, where if there is n particles and we want to distribute n particles in k bins, so that the total number of combination will simply n plus k minus 1 is combination of k minus 1. Okay, so this is nothing but the total number of microstates for our problem. Okay, where n is the number of particles and k is the number of basket. Now if you simply substitute this into a formula, which will gives you 3 plus 3 minus 1 3 minus 1, and if you calculate this will gives you 10. So then the correct answer will be the option A, 2 and 10, right? So problem number 2 is done. Okay, now we goes to the problem number 3. You let me write the problem first. So using Boltzmann distribution of an oscillator occupying the first two levels, that is n equal to 0 and n equal to 1, is found to be 0.637 and 0.223, and the probability of oscillator energy in energy level n greater than equal to 3 is 0.042. Then what is the probability in n equal to 2 levels? Okay, and let me also write the options. Option A is 0.902, option B is 0.420, option C is 0.098, and option D is 0.000. So we have to find out the correct answer. Okay, now before doing the problem, let me just discuss what is this Boltzmann distribution and what are this energy level actually means. Okay. So Boltzmann, it's basically it's describes the probability of particles occupying different energy levels in a system at a given temperature. Okay, so what Boltzmann distribution basically gives you the probability of occupying different energy level in a system at a given temperature. Okay, so here what happens, here you know it's the oscillator, right? So oscillator you already know it has different energy levels, right? N equal like this, like in quantum mechanics also, like n equal to 0, n equal to 1, n equal to 2, n equal to 3, and each of these levels has a specific energy values, right? That is also you know. Now in this problem, the probability of occupying one of this state with a finite energy is basically described by this Boltzmann distribution. I mean the probability is basically explained by this Boltzmann distribution. Okay. For this problem right now we don't require the exact expression of this Boltzmann distribution, but okay, anyway, so in the next problems we will actually have to use the form of the Boltzmann distribution. So in the next problems we'll discuss more about this, but for the current problem, uh, the values of the distribution, like values of the values of the probability of at n equal to 0. So probability at n equal to 0 is mentioned at 0.637, and probability at n equal to 1 is 0.223, and probability n equal to greater than 3, that means the probability that it has energy greater than 3 or greater than equal to 3 is 0.042. So these are the probabilities that are already mentioned in the problem. Now you have to find out what is the probability of n equal to 2. That means what is the probability of having in n equal to 2 state. Okay, so how you can calculate? You already know the total probability will be equal to 1 simply, right? So that means P of n equal to 0 plus P of n equal to 1 plus P of n equal to greater than 3 plus P of n equal to 2 would be simply equal to 1, right? And all this individual probability apart from that probability at equal to 2 is already given, right? 0.637 plus 0.223 plus 0.042 plus P equal to n equal to 2 is given 1. So from this thing simply can calculate this 1 minus 0.637 minus 0.223 minus 0.042. Okay, after you calculate this, so if n equal to 2, it simply gives you 1 minus 0.902. This is basically 0.098. So this will be simply gives you the probability of the oscillator being in the probability. So this is basically the probability of the oscillator being in the n equal to 2 level is 0.098. Okay. Okay. Now we'll do the problem number 4. So problem number 4 basically asks you, when t tends to 0, value of the single particle partition function will be what? That is given. That is option A is 1, option B is infinite, option C is 0, option D is summation of Gj. Provided that the degeneracy of level degeneracy of level J is equal to Gj. This is the degeneration of level J, which is given as Gj. So this is the given problem. Now in this problem, now in order to solve this problem, some concept about statistical mechanics first you need to know. You need to have a good idea of it. And one of the important things is called as partition function. So let me try to write it. Okay. So the partition function is a fundamental quantity in statistical mechanics that encodes the statistical properties of a system in thermal equilibrium. So this thing is very important. The system needs to stays in thermal equilibrium in order to calculate the partition function. Okay, so this is one point. So next point is uh, uh, so next point is it plays a very crucial role in determining the thermodynamic quantities like free energy, entropy, average energy. Okay, these are the quantities that you can calculate if you know the uh, partition function of a system thermodynamic equilibrium. Then using that partition function, you can basically calculate all of these quantities like free energy, entropy, average energy, all these things. Okay. Now let me write the expression of partition function. Okay. So for a system with discrete energy level EJ and degeneracy GJ, the canonical partition function is given by z equal to gj e to the power minus beta ej. This is the expression of partition function given. Okay, now in this expression, this e to the power beta j is basically the Boltzmann probability distribution, Boltzmann distribution that we have discussed earlier, right? This is the Boltzmann probability in EJ. Okay, beta is basically 1 by kBT. T is the temperature, because this system needs to attain a particular temperature, right? Gj is the degeneracy here. Like degeneracy means if the system's J has any degenerate energy level, like inside the system having like degenerate energy level is having a energy value EJ, then that means that system, that energy, particular energy, have some degeneracy. And if Gj is the number of degenerate energy level, then Gj is the also is called the degeneracy for that particular energy Ej. Okay, so degeneracy of Ej, and this is for continuum system. And for continuous system, this z will be simply Ge into e to the power beta ETE. This is for discrete system, this is for continuous system. Okay. Now if you have this z value, you can calculate many things. If you have this z expression. Okay, first thing you can calculate is called free energy, or the Helmholtz free energy. That is, I guess you already know, if the free energy is kBT ln z. Similarly, second thing you can calculate is the average energy. That is basically the average energy of the system. Okay, E is basically minus delta ln z by delta beta. Third thing you can calculate entropy. The expression is simply S equal to kB ln z plus beta E. It's a constant function of energy. Beta is basically. Also you can calculate specific heat, or sorry, heat capacity, which is CV equal to del E del T. So all of these things you can calculate if you get hold of this partition function Z. Okay, so this is a very important when you are studying any kind of statistical properties of a system. The first thing that you have to calculate is the partition function, canonical partition function, if it's a canonical system, definitely, or microcanonical system. So if you get able to calculate this in this, if you get to hold this partition function for the system, using that partition function you can calculate all of these quantities. Obviously the system has to be in a thermal equilibrium state. Okay, all these formulas are only applicable in thermal equilibrium. Okay. Now for our problem, what we have been asked to do, uh, we have to calculate the for single particle. For single particle case, what would be the partition function at t tends to 0 value? Okay, so now how we can do that? So we already tell you that z is equal to summation of j gj e to the power beta ej. Now if as t tends to 0, that means in the problem it's mentioned that t tends to 0, then you already know beta, that is equal to 1 by kbt also tends to infinite, right? So if I 1 by kbt it also tends to infinite, then e to the power beta ej, so this value, so if beta tends to infinity, then e to the power minus infinity, so that means e to the power infinity, that gives you 1 by sorry, this would be e to the power minus, so e to the power infinity is 1 by infinity, this gives you 0, right? So this basically in the limit t tends to 0, this also tends to 0. So the right answer would be t tends to 0, z tends to 0 in the limit of t tends to 0 limit. Okay, so this is how you have to solve the problem. Okay, so what we have learned, so first this is the actually z is basically called a canonical partition function. Okay, so if a system consists ej degenerate levels, ej discrete degenerate level, let's suppose each energy level has a degeneracy of gj, each energy level, then their partition function is basically given by this quantity. This is the probability, Boltzmann probability distribution. Beta is the 1 by kbt and gj is the degeneracy, and for a continuous system we have to write the integral part of this summation basically, which will be this. And now if you know this j, you can calculate many things: free energy, avoid energy, entropy, heat capacity, all of these things you can calculate if you know the j expression. But in our problem we have been asked to find out for a single particle what is the partition function. Okay, this is the partition function, and the limit will be at t tends to 0. Okay, so any whatever the number of particles is, if t tends to 0, beta also tends to infinite. So if we put this beta tends to infinite in this problem, so this basically gives you this whole thing is tends to 0. So the z will be basically tends to 0 in the limit of t tends to 0, right? So this is the problem. So this is the fourth problem, right? So I hope all of you understood how we are basically solving this problem. The next is problem number 5. Okay, So the sample of atomic oxygen at 27°C, what proportion of atoms are in the first excited electronic state if it lies 1000 kilojoule or mole inverse above the ground state. So this is the first problem. Okay, the options are A is option A is 0, option B is 10 to the power 400.93, option C is 10 to the power minus 174.09, option D is e to the power minus 174.09. So okay, so option C and D are basically they are given equal here. So anyway, so in order to solve this problem, we have to basically use the Boltzmann distribution. Okay, let me write a Boltzmann distribution properly here. Okay, so answer. So if there are two states, let's suppose one is the excited state, one is the ground state. Let's suppose there is total n number of particles, and out of this n number of particles, n ground is, let's say, the number of particles that is in ground state, and n excited is the number of particles that are in excited state. Ground plus n excited. So where delta E will be equal to simply 1000 kilojoule per mole. Okay, so like the energy interval between these two states will be basically delta E. Delta is 1000 kilojoule per mole. Okay, now in case of a Boltzmann distribution, the ratio of this n excited and n ground, number of particles in excited and ground state is related by this formula, E of minus delta E by kBT. Okay, so this is it. Now if you want to calculate this, delta E we already know is 1000 kilojoule, and kb we already know 8.314, and T is here. So in the problem itself, T is at 27°C, right? That means at 1000 Kelvin, right? So sorry, 300 Kelvin, right? So kBT will be simply 8.314 into 300. So this, as T is 300 Kelvin, so this is the value of kVt. Okay, so delta E by kVt is 1000 into 10 to the power 3 into 8.314 into 300, basically 10 to the power 6 into 2494.2. that simply gives you 400.93. Okay, so n excited plus n ground basically gives you e to the power minus 400.93. But in the problem, but in the so in the answer there is basically they are written it in terms of 10 to the power. Okay, so this can be done. Actually you have to change the base. Okay, so this is actually you can do it. So in order to do it, we have to simply change the base of this exponent. So we can write this thing like this, right? E to the power minus 400.93 simply can be equal to, you can write it like this, 10 to the power 400.93 into ln. Ln means log e base. Okay, ln means log e base 10. Okay, this we can write it like this, right? So because we know that e to any, like we can e to the power, let's suppose 4, we can write it like this, 10 to the power ln e base 4. Okay, we can write it basically like this, e to the power 4. Simply e to the power minus 4, you can write it like this, 10 to the power then in that case it would be minus. Okay, so okay, so so this way we are writing this. So now since ln 10 is 2.302, we can write it nex by ngr is equal to 10 to the power 400.93 by ln 10, that is 303 by 174.09. Okay, so 10 to the power minus. Okay, so the value of nex by ngr is simply 10 to the power minus 174.09. So the correct answer would be this. Okay, so all of you understood. So basically in an oxygen atom there are two energy states. One is the ground state and one is the excited state. And the excited state is 1000 kilojoule per mole above from the ground state, and at 77 degrees centigrade temperature you have to find what are the fraction of particles that are in the excited state. How we can do that? We can simply use this Boltzmann distribution in order to find the number of particles in excited state compared to the ground state. And this is the formula, and this is if we substitute delta E and kBt, this is the 400.93 we are getting. So in excited way, in ground is minus 400.93. So this is the expression. Now if we now in the answer everything is written two of the answer is written in terms of 10 to the power, but we are getting e to the power, so we have to change the base. So we are using the formula of logs, and from there itself we are getting this as our final result, which is matching with the option C. Okay, so problem number 5 is done. Now in the assignment section, for assignment 5 section, we have covered all the problems. Now as we still have some time, almost around 40 minutes, so we will now discuss some problems about the previous assignments, like assignment 2. Okay, this is assignment 2 is already done, I guess. So we will discuss some of the problems, okay, from assignment 2. Okay, so so problem number 1, assignment 2. Problem number 1, identify x and y in del h del p at x, del g del x at y. Okay, options are option A x equal to t, y equal to v. Option B is x equal to v, y equal to p. Option C is x equal to v, y equal to t. Option D is x equal to p, y equal to also t. Ah. Now how we can solve this problem? Okay, so uh, H is basically here means the enthalpy, right? So 1 second. So first, the enthalpy expression you already know, right? A is equal to U plus PV. Now, but here we write it in the differential form, right? So, H is 30. So, dH is equal to du plus PdV plus VdP. Now, we already know dq equal to du plus dw, that means du plus PdV dq. Now, du, that means will be dq minus PdV plus VdP dH. PdV will cancel and dq already know is cv dt. So, sorry, dq is TdS. Yes, that I've written it was for du actually. So this is dq. So we write TdS, PdV will cancel, PdP dH. So this is the differential form of enthalpy. Now what you have to do? Now here you have to first take so next you also need the Gibbs free energy, right? So called Gibbs free energy. For Gibbs free energy, G is U plus PV minus TS. Okay. Similarly, here also D is equal to DU plus PdV plus VdP minus TdS minus SDT. So equal to du plus dw or du plus pdv. So du is dw already know. So sorry. So here it will be du will be simply tds minus pdv. So du you can write is tds minus pdv plus pdv minus bdp minus tds minus sdt. So now we can write it like, so tds cancel, pdv cancel, so plus pdv, so minus sdt plus VdP. This is the differential form of Gibbs free energy dG. Now we have to find out what is this x and y in this derivative. Okay, this x and y you have to basically find out. How can you do that? So in order to do that, first this side all of the things are given. This side everything is given. So del H del P at constant S. So here from the expression of this we can calculate del H del P at constant S. So del H del P at constant S will be simply uh, V, right? This will be simply V for this term, right? This term will only contribute. Okay. Similarly, we can also calculate del G del P at constant T. So del G, this is the expression of Gibbs free energy. This is the expression of Gibbs free energy. If you do the del G del P at constant T, this basically gives you this also gives you V. Okay, so that means del H of del P at constant A is will be del G del P at constant T. So if you compare this thing with this expression, this will basically gives you the value of x and y, and this problem the x is P and y is T. Okay. X is P and y is T. So the correct option will be this option T. Okay, so I hope all of you understood. So this type of problem also I have done previously. Okay, so basically this x and y you have to find out. So in order to do this, you have to know these two form of the Gibbs free energy and Helmholtz free energy, and from there, if you take the partial derivatives of del G, del H, del P at constant A, you have to find out that by doing what derivative of Gibbs free energy you are getting this volume V. And we have find out that if you do del G del P at constant, you will get a volume which is exactly del G del P at constant will be equal to del H del P at constant S. So that means the x will be P and y will be T as an answer. Okay, that's it. Now we move to the problem 2. So problem number 2 we'll discussing. So 1 mole of oxygen expands adiabatically against a constant external pressure of 1 atm until the pressure balances again. The initial temperature and volume are given as 200 degrees centigrade and 20 liter respectively. Now we have to find out the changing entropy. Okay, so okay. Hmm. So given that N is 1 mole, T1 is 200 degrees centigrade, that is 473 Kelvin. V1 is 20 liter, that is liters is given, and P2 is 118. Okay. So like here the thing is like under a constant external pressure of 1 atm, the gas expands, and the initial temperature and volume are given at 20 degrees centigrade and 20 liter respectively. I have to calculate the change in entropy. Okay. Okay, so this is the given problem. So how we can calculate that? Okay. So uh, P2, that is the external pressure. Okay, that is 1 atm. That means that the pressure is balances with the external pressure. So that means uh, here, that means the final pressure is mentioned, that is P2 is 1 atm. But we can, using T1 and V1, we can calculate initial pressure, right? Which is also needed for a problem to solve it. Okay. So P1 is, we can P1 V1 equal to nRT1, right? So we can calculate it, P1 equal to nRT1 by V1, T1 by V1. So 1 into 0 0.08206 into 473 by 20 liter. So P1 is 1.941 atm. So P1, this is, so now this process is an adiabatic process, right? For an adiabatic process, first what we will do, we will write the uh, uh, equation, like first law of thermodynamics, that is delta equal to delta Q plus delta W. As this is adiabatic process, so delta Q will be equal to 0. Now actually we are doing this because we have to also need to know the temperature at the end, because temperature is also, because everything is changing actually within the system. Okay. Pressure, initial temperature, and volume, initial volume, all of these things are given, and pressure is also changing. So three things we have to calculate how it's changing basically. So in order to calculate the change in temperature, we can easily do it. Okay. We already know in CV T2 minus T1 equal to minus P external P2 minus V1, that is delta U here. Now as this is a oxygen, so that's a diatomic gas, so Cv is nothing but, you already know, 2 plus half into R, n plus half into R, as here n equal to 2, the reason is it's a diatomic, so Cv equal to 5 by 2 R, so n into 5 by 2 R T2 minus T1 equal to P external, that is P2, V2 minus, so minus is there, nR T2 minus P2 minus nR T1 by P1. Now 5 by 2 T1 minus T2. I just absorb the negative sign in the left hand side. This will give you nR T2 minus T1 by P1 by T2, because T2 we not know, so and we multiply P2 in both sides, so this gives you 5 by 2 473 minus T2 equal to T2 minus 473 into 1 by 1.941. okay, now if you solve this, this will basically gives you T2 equal to 407.48 Kelvin. So this is how we'll get the value of T2 here. Okay, so this is the T2, so we get the P1 and so get the T2. Now as both pressure and temperature is changing during this process, so both of these change basically will be contributing into the change in the entropy of the system. Okay, so now the change in entropy of the system is delta S, right? And the expression of delta S is given, delta S equal to NCP ln T2 by T1 plus NR ln P2 by T1. Now delta S is simply 1 into 7 by 2 by Cp comes from actually from this, we know Cp minus Cv equal to R, right? And here Cv is 5 by 2, the Cp is simply R into 5 by 2R, so this gives you Cp is 7 by 2R, and by 2R ln 407.48 by 473 minus nR. N is here 1 more, so N here will be also 1 into R. R is already 8.314 into ln. Here pressure was at the final is 1 atm and initially is 1.941, because that we have calculated earlier. So now delta S would be simply, if you calculate both this term, this will gives you simply 1.172 joule per Kelvin. So this was the corrected answer for our system. So I actually forget to write the options, but this is how you should calculate. Okay, this is the correct answer. Okay, so here basically 1 mole of the problem is expand adiabatically at an external pressure on a team until the pressure rise. So initially the pressure was different from the external pressure, and initial temperature volumes are also given respectively. So first what you have to calculate, what are the final, all the values of final initial pressure, temperature and volume. Okay. And for the pressure, we can easily calculate it using the Charles law. Okay, P1 equal to N at T1. That gives you the value of pressure initially. Next, you also need the temperature, final temperature T2, and that is also we can do using the first law of thermodynamics. We have done here, and this is the final value of T2 we are getting. Now, since both the pressure and temperature is changing, so it will contribute into the total change in the entropy. Now the total change in the entropy will be in Cp ln T2 by T1 and nR ln P2 by P1, and if you calculate this Cp already know, this is the diatomic molecule, you calculate the Cv, and from there we can calculate the Cp, and this is the value of delta S we are getting after doing all the calculations. So this is now problem 2 is done. Okay, now we'll go to the problem 3. So now problem 3. So in problem 3, you have to calculate the maximum entropy of mixing achieved when two ideal gases X and Y are mixed. So let me write maximum entropy. That we actually, this type problem also have done previously. The entropy of mixing basically we have to calculate. The maximum entropy of mixing is achieved when two ideal gases X and Y are mixed in the amounts of options here 1 mole of X and 3 moles of Y. Option B is 3 moles of X and 1 mole of Y. Option C is 2 moles of X and 3 moles of Y. And option D is 2 moles of X and 2 moles of Y. Now this kind of problem already discussed, right? So basically we have to calculate the entropy and mixing, and under which process the entropy is maximum will be the correct answer. Okay, so 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 entropy of mixing delta S mix, we know the formula is minus nR xi by ln xi. So xi is basically fraction of ith, and more precisely xi is mole fraction, right? Mole fraction of ith component of a mixture. So basically what happens, let's suppose there are two gases, 1 and 2, which are separated by this insulated wall, and when you remove the wall, these two gas will mix up, which actually enhance the entropy of the whole system. Okay, this is called the entropy of mixing, and this is the formula of delta S mix. I mean the amount of entropy that is incremented due to the mixing process. Now for each of these four options we have to find out which case the entropy will be maximized. Okay, so the option for option 1, one mole of X and 3 mole of Y is mixed. So in this case N1 is 1 and N2 is 3, so X1 will be 1 by 4 and X2 will be 3 by 4. Okay, and delta S mix will be minus 4R x1 ln x1 plus x2 ln x2. So this will be minus 4R 1 by 4 ln 1 by 4 plus 3 by 4 ln 3 by 4. This will give you minus 4R 0.346 minus 0.215. This will give you 18.69 delta S mix. Next option is option 2, that is 3 moles of X and 1 mole of Y. Okay, so here N1 is 3 and N2 is 1, so X1 will be 3 by 4 and X2 will be 1 by 4. Okay, this will be gives you a similar answer, right? Previously it was 1 mole X, 3 mole Y, and 3 mole X, 1 mole Y. Here also delta S will be same, 18.69, right? 18.69 joule per Kelvin. So it will also joule per Kelvin. Okay. Now we go to the option number 3. Option number 3 is 2 moles of X and 3 moles of Y. So so basically here N1 is 2 and N2 is 3. This gives you X1 equal to 2 by 5 and X2 will be 3 by 5. Okay. Now for this case, delta S mix will be minus 5 by R 2 by 5 into ln 2 by 5 plus 3 by 5 into ln 3 by 5. This simply gives you minus 5 by R into minus 0.36685 minus 0.3064 delta S mix, which gives you 27.97 joule per Kelvin delta S mix. Now the last is the option 4. 2 moles of X and 2 moles of Y. Ah. So this is the last option. So now so here N1 is 2 and N2 is also 2, which gives us x1 equal to 1 by 2, x2 is also gives 1 by 2. Now in this case delta S mix will be minus 4R 0.5 ln 0.5 plus 0.5 of ln 0.5. So this basically gives you delta S mix 23.05 joule per Kelvin. Okay, so now I have to compare all of the answers. So from the first two mixture we get intensity 18.69, 18.69. Next one we get 27.97 and last one we get 23.0. So out of this, in the three combination where 2 moles of X will mix with 3 moles of Y, in that case the total change of entropy was maximized, right? So the correct answer for this problem would be option uh, C, right? Option C. So question number 3 is done. Now we move to the question number 4. The problem number this is the problem number 3. Now problem number 4. This is a basically statement you have to show whether it's a true or false. Okay, the statement is the entropy of the universe for a reversible process remains constant. Okay, now you have to tell whether this statement is a true statement or it's a false statement. Okay, now how can you do this? So this is very easy, right? Because uh, you already know that for a reversible process, delta is total, that is total change of the entropy, because when a process happens both the entropy of the system as well as the surroundings both are changing, right? So the total change of entropy during a reversible process, but for reversible process the total change will be equal to 0. So now what you can do, that you have to actually show. Okay, how we can do that? For a reversible process we already know that change in the entropy for system will be equal to the minus of change in the entropy of surroundings. Okay, now the total change of entropy, delta S total, will be simply the delta S system plus delta S surroundings. Now for this case, for our problem, delta S system simply equal to delta surroundings. So if we substitute it here, so delta S total gives you as these two equal, this gives you 0. So total change in the entropy will be the entropy, total change in entropy will be 0. So this means entropy S, if the change is 0, then entropy will remain constant. Okay, this is our last one. Okay, so I hope all of you understood how we're solving this problem. So initially in this session we have discussed initially the problem of random walk. Okay, like just only 1D random walk. Okay, so what are the distribution that is governed by 1D random walk, and how the mean square displacement, how to calculate the total displacement, all these things we have calculated, we have shown up in the properties of the random 1D random walk. Next we calculate some concept about microstate and macrostate in terms of balls which you want to distribute in 3 similar basket, and from there we have calculated microstate and macrostates. Next problem, similarly there is energy level of oscillator, and we have calculated the probability of getting the energy of the oscillator at different energy levels. Similarly, we have used here the concept of partition function to calculate the I mean at t tends to 0 limit, you have calculated the partition function of single particle. And next you have also calculated if the particles are distributed into in a thermal system, in a classical thermal system, uh, uh, in a ground state and excited state. So we can easily calculate using the Boltzmann distribution function what is the ratio of the particles in the ground state and excited state. So this is basically the formula. So these are the basically things that we have learned during this session. So I hope all of you understood. Okay, so uh, let me just close the session. Okay. Stop the recording.